So let's start. Today we're going to talk about neural network. Anyone has done any revision for neural network before coming to class today? Okay, very fast question. Do you remember what perceptron was? Perceptron? It sounds like Transformers movie, right? Perceptron. But what is perceptron? Perceptron? Feel like now everyone looking to the screen or what now is asking about. So what is perceptron? Consists of one layer, right? We have single layer where you have one or more TLUs, thread logic units, or in other words, neurons. Neurons, where every neuron is connected, fully connected to the input layer. And we have, right? This is, we call it dense layer. So again, we repeat, perceptron is one layer of TLUs, meaning one layer of one or more neurons or threshold logic units. Each of these TLU, like this example, the orange one, these are the TLU. The blue one are not TLUs, huh? The blue one are not TLUs. These are input. These are the values of the input that you're going to feed to the network. So the TLUs here in this picture is the orange. In this picture, the purple and orange. These are TLUs. The blue one are just input. Okay, so now this is perceptron. This is not perceptron. This is multi-layer perceptron. This one. Okay, so this is a single perceptron. I mean, this is the concept of perceptron where you have single layer. So we have only one layer, which is the output layer only. Of course, this is also, you can call it input layer, but the point is we emphasize about the TLUs. So TLUs only exist in hidden layer and output layer. Input layer, just the values coming from the data set. Every neuron or TLU in particular layer connected to each neuron in the preceding layer. In this case, of course, we have only input neurons. I mean, coming from input layer. This is configured, referred as fully connected or dense layer. Okay? I look at faces, but remember, if you like to ask direct question, you may, or go to the Padlet and post your question there. If you feel shy. By the way, shy in Arabic, I mean, if you say shy in Arabic means tea. So sometimes I just make joke, don't be shy, don't be coffee. So this is because of the language. Okay, so if you have a question, just you can ask. Okay, so any question about perceptron? If you have, you can post your question or ask directly. So perceptron implementation already provided inside scikit-learn. By the way, this is the whole code in this practical coming from chapter 10 of the second part of your book for neural network. If you like to refer to your book, you can. Then there's another 9 chapters if you like to read on your own or related to deep neural network. We are only covering the tip of the ice in chapter 10. Only taking the introduction to artificial neural network for the lecture and also for the practical session. So perceptron is already, the implementation of perceptron is already provided inside scikit-learn. We load our iris dataset, the famous dataset, and we are interested only in 2 variables. We're taking betal length and betal width. Okay, the other 2, we don't need them. So now just we are looking for 2 variables, input variables. And we are interested to build perceptron that is able to recognize setosa only. That is able to recognize setosa only. That's why we check if the target equals 0, that means it is setosa. Otherwise, it's going to be false. So Y is going to be an array of true and false. True means the flower, the corresponding flower is setosa. False mean no, not setosa. So it is binary classification. We have only 2 classes. Originally, iris dataset is multi-class, but now we make it again binary classification because of this line. Because of this line, it has become binary classification problem. Now we create an object from perceptron, and then we fit our dataset. By the way, neural network is supervised learning. You see, we have to provide X and Y. So neural network is supervised. Fit. After we fit, we can predict. So we provide information for 2 flowers. Their betal length and betal width. So this is the first betal first flower, petal length, petal width, and the second one. Then we predict the output is going to be true and false. True indicate the first flower is setosa. The second flower is not setosa. Binary classification. Okay? But what is the weakness of perceptron? What is the weakness of perceptron? Badminton guys? What is the perceptron? What is the weakness of perceptron? People are about to fall asleep. Perceptron. Then you close your eyes and then see some dreams. Perceptron following you. So what is perceptron? What is the weakness of perceptron? If you check back the slide, it's all there. Where were the slides here? So where's perceptron? Yeah, the weakness of perceptron, the inability to solve nonlinear problem. That means only it's able to work on simple problem. If you have complex problem, then perceptron won't be able to help. In this case, what we need to do for nonlinear problem, for complex problem, we need to go with multi-layer perceptron, not only single layer, because perceptron is only single layer. So we need to make it complex. How to make it complex? We add more layers of perceptron. So here, as this example show you, now we have 2 layers of perceptron. Okay? The first layer is input, right? First layer is input. This is the first hidden layer. We have only single one, and output layer. So perceptron, in other words, here already mentioned, consists of 1 input layer, as you see here, then followed by 1 or more intermediary layers, or we call them hidden layers. Here we have single hidden layer. And finally, we have 1 output layer, this one. So we repeat multi-layer perceptron. We have 1 input layer, right? We have 1 or more hidden layers, and then we have output layer. In perceptron, what do we have without multi-layer? If we have just perceptron, we have only input layer, output layer. That's all. So you see here, we have input layer, output layer. There's 0 hidden layers. Okay, no hidden layers. In multi-layer perceptron, you have 1 or more hidden layers. Clear? Now this network is more capable. This network is more capable of handling complex problem than this one. This is only input, output. This one has some hidden layers in between. Okay? Clear? Now the concept deep neural network comes by adding many hidden layers. So if you have maybe 5, 10, 20 hidden layers, then it becomes deep neural network. Understood where the word deep comes from? Where you stack many hidden layers inside. Then it becomes deep neural network. Understood? So what is deep? Not deep sleep. Deep neural network. Okay, so let's come back here. So in order to use multi-layer perceptron, also the implementation is provided inside scikit-learn. We have MLP, multi-layer perceptron regressor for regression problem, and we have MLP classifier for classification problem. So let's show fast 2 examples. Here for this example here, gonna work on California housing. So our target is to predict housing price. So this is regression case. We need to use MLP regressor. So we get the data here, all the housing data, where this one includes data, the input features, and target, which is the output feature. Then we split our data into training set and test set, all right? After we split, we need to prepare the validation set. This is why we split further our full training data set into training set and validation set. Clear? So on these 2 lines, we have prepared training set, validation set, and test set. Okay? Anyone would like here to come and explain? If you like. Simple, huh? No, not difficult. Then I help. I can become your assistant. Just come here. Then when you struggle, just look at me, then I talk. Anyone interested to become lecturers for 5 minutes or 1 hour? Up to you. We can make extension if you like. Nobody, huh? Okay. Then we come to create an object from MLP regressor. And then we need this MLP regressor, same MLP classifier, has one argument called hidden layer sizes, right? Now, since we are working on MLP, that means we have hidden layers. So you need to specify the hidden layers. What does it mean here, 50, 50, 50? Any idea? Just what do you think? Talk. Like in that movie, he told them, say something. He say what? They just say something. So what do you think? What does this imply? Firstly, how many values do we have here? 3, right? That means we are asking MLP regressor to create 3 hidden layers. Each hidden layer has number of neurons. Here we specify the number of neurons for each hidden layer. So 50 here means the first hidden layer has 50. The second hidden layer also has 50. The third hidden layer also has 50. If you like to change, up to you. This is, you can tweak and change around. Maybe you put here 100. Maybe this one 75. This is 50, for example, up to you. Usually the first hidden layer will have higher number of neurons. As you go deeper, then the number of neurons will become lesser and lesser. Okay? And remember, also already provided to you inside the slides, if you're not sure what value, you can decide the typical value for regression for hidden layers from 10 to 100. So here we already provided 100, 75, 50, but that doesn't mean only these values. Can you go to 1,000? Yes, can. It depends on the complexity of the problem. Okay? Then we prepare our pipeline. We add standard scalar along with MLP regressor. Why do we need standard scalar? Standard scalar indicates what? What are we applying? Standard scalar means we are applying what? Feature encoding. Feature what? Feature. I cannot see the lips, so I don't know what you're saying. Unless if you remove the face mask, then hopefully I'll try to recognize doing face recognition. Sorry, lips movement recognition. So what does it imply? Applying standard scalar, meaning we have feature scaling. Very good. So we are doing feature scaling. That indicates what? That the neural network is what? Is sensitive, right? Remember, we apply feature scaling because some algorithms are sensitive toward the input value range that you provide. So neural network is sensitive toward the input values. This is why we need to apply feature scaling first. Then we call fit, finally predict. We can calculate mean square error. Okay? Any question? Let's look to a case. Again, if you feel shy, please go here and write something. Already I got few questions from morning session. The noon session, no question. Let's see evening session if you have any question. So for classification, let's look back to IRIS dataset. So again, we got the full training data and test. We split, sorry, after we get the data, we split into training and test. Then we split further into train and validation. So we prepare train, validation, and test sets. Then we create an object from MLP classifier. We provide hidden layers. Here we got only value of 5 indicates we have only one hidden layer with 5 neurons. Okay, max iteration refer to the epoch. Epoch in this case here. Then make pipeline, standard scalar, again, same. Fit, and finally we calculate the score to predict. Sorry, the score, which is accuracy in this case. If you are using classifier, then when you call score is going to give you back accuracy. If you are using regressor, when you call score, then you're going to get R squared. Okay, you can check the documentation also, they're going to tell you. So score is available for all algorithms. In order to know whether the score has been given to you, whether it's accuracy or R squared, you need to check the algorithm. If the algorithm is classification, then it's accuracy, otherwise it is R squared. Okay, Then we prepare our pipeline, same, then we fit and predict. Now all of you now understand what is perceptron, MLPs, but MLPs also the implementation from scikit-learn has limitation. If you have complex problem, then MLP from scikit-learn won't be helpful. So if you have complex problem, then you need to look for something else, not scikit-learn. You need to look for TensorFlow. So this is why here we're gonna apply next, applying TensorFlow for the following problem. Okay? Yo when tima. Yo when tima. Okay, for this example, we're gonna use fashion MNIST. Remember last time on lecture, or sorry, practical 6, we used MNIST, right? Do you remember? Or already forgot? After practical test, wipe out, remove everything. So in MNIST, we were looking for the handwritten digits. So earlier we built classifier to classify the handwritten digit into the correct class. Correct? This is back in practical 6. But today we're not looking for this MNIST, we're looking for fashion. Fashion MNIST is about clothing. So we have pictures for clothing available. Let's take the background, the white background. And then if we look also, there's a, you can look for fashion. Not this one, TensorFlow. Okay, so again, it's about clothing, pictures available inside the data set, and this data set is labeled. In addition, we have, I think this is a different one than yesterday I found TensorFlow. Keras. Okay, this works. So this data set has how many classes? We have 10 classes. So the data has already been labeled for us, provided, and we have 10 classes. So we're going to use this fashion MNIST data set available inside Keras for the following example. So still no question. So firstly, make sure you import the TensorFlow. Then from TensorFlow, you navigate to Keras, datasets, and then fashion MNIST and the function load data. We call load data. Now, once you call load data, actually the people who implemented this function have already splitted up the data into the training set and test set. Again, I'm not calling train to split, and why I'm doing this, not because I like to, but people who implemented this function, they make the data set available in training set already and test set. They already splitted the data set for us. Then I would like to take some portion of the data set as validation set. So here, what is the size of validation set? Anybody can tell? What is the size for validation set? Just looking to this line, even if you don't know what is the size for the full training data. Yeah, exactly, 5,000. So here we're taking the last 5,000 picture from fashion MNIST, from the training set to be validation set, under validation set. And then the remaining is going to go for training. Actually, this data set, if you check the X full data, training data set, has 60,000 pictures. We have 60Ks of pictures for all 10 classes of fashion clothing. So this is the first value here. How about the second two values, 28, 28? What does it mean? Yes, correct, pixel, but 28 means? Yeah, very good, pixels, but what do we mean by 28? By 28? Number? Sorry, number? Byte? Okay, byte. But byte, okay, each pixel, yes, correct. It's gonna store it in 1 byte. But again, what is the point here? It tells us 28 by 28. Sorry? I cannot hear, just if you speak up. Okay, width and height, yes, correct. So in other words, we're looking for number of lines of pixels, 28 by 28. So in other words, the size of the photo is 28 pixels by 28 pixels. Would you like to count the pixels yourself? Kana, by the way, if you check here, but we don't know the dimension. So if we take here, let's say we have, if you take out, okay, let me show you. So make sure first you run this part. Okay, anyone interested to count? Let's see how many pixels. By the way, the pixels here, those circles, the squares, you see those little squares? Each one of these represents 1 pixel. So let's count, shall we? Let's take full line here, like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Sorry, this is 27, 28. So we have 28 pixels per line, and also how many lines overall? 28 as well. So the size of the picture is 28 by 28, if someone doesn't know yet. Then we need to do normalization. We already said that neural network is sensitive toward the input range, the value range, right? So we need to do normalization. This is why we divide all the training data and validation and test data by 255. Why 255? Why we need to divide by 255? Why not 100? Maybe 125 or 300? Or why not we take 1000? Why it's 255? What is the pixel range? Any value if you take from this screen. What is the value for pixels going to be? In number, as a numeric. Sorry? I cannot hear. RGB, yes, for colorful. But if we take, let's say, red alone or grayscale, what is the value for each element is going to be? Between 0 up to 2, 5, 5, right? 255, between 0 to 155. If you're not sure, would you like me to prove? Then let's take one picture from X-ray. Let's look to its value. What you notice? That all the values fall in range between 0 and 255. You're still not convinced? You can look for NumPy. P.min and P.max. So 0 up to 255. Okay, very well. Now we know. But why we divide by 255? Now we know maybe it's related to this value. But why 255? Do you remember when we studied feature scaling? There was one scalar called min-max scalar. Do you remember that? Min-max. What was the equation for min-max? The equation where you take each value as a pixel, subtract by the x-min, which is 0. We already know the minimum value for any pixel is 0. So we still have on denominator only x divided by x max, which is 255 minus 0, 255. So this is why just we end up here dividing by 255. Okay, clear? So now you understand why it's divided by 255, right? So basically we are taking min-max scalar and we have 0 for min and max is 255. Then we normalize our data. Here this code will show you what the picture is. So for example, if we print out the first picture, then we can see it. For example, what is this? What is the first picture? If we don't know, that's fine. Then we look into the label, right? Because this data is labeled. Then you look into train, y train 0. Y train 0 is 9, correct? Has the label 9. Checking back the data set, 9 means ankle boot, okay? 9 means ankle boot. So this is ankle boot. How about something else? Let's take the first or the second picture. This is should be t-shirt. So t-shirt has label 0. If we check back, 0 means t-shirt. Okay. Why suddenly we are here? Oh, this. Anyway, the classes has already been provided to you here, the classes names. So if you like just to check what class name you have here, the corresponding class for the label value, then just you can use this line. So again, for 1, it is t-shirt. But make sure you run this line first, then this one. Okay? So now just we understood our data set. We understood our data set. By the way, is this binary, multi-class, or multi-label, or multi-output classification problem? Let's see. Again, I repeat, what is the problem we have in hand? Is it binary classification, or multi-classification, or multi-label, or multi-output? If you remember, we discussed this during practical 6. There are 2 questions you need to answer in order to determine the type of classification you're working on. The first question is, how many labels you have? So if we check here, how many labels do we have? How many labels? Anyone can tell? How many labels? 10. Okay. Anyone else? Good try. Anyone else? How many labels? In order to know, actually, it's very simple. You know how? If we take just like the first picture, how many values did we get here from Y train? How many values? Only 1, right? Since it's only 1, that means we have single label. Only single label. If it is two labels, for example, then you should have here 0, 3, for example. Or maybe it is, we have 3 labels, then should be maybe 0, 1, 3, 10. I don't care. But the point is, Y train, when we call for 1 picture, so this is corresponding for 1 picture, correct? We have single value. Since it is single value, means it is single label. Since it is single label, then we can rule out multi-label, multi-output. So both of them away, out, correct? Since we have single label. Now we look to the second question. How many classes do we have? Like what your friend just now said, we had 10. So his answer for 10 was for the answer for the question, how many classes? So we have 10 classes, correct? How to know? So we check how many unique values we have inside the data set. So if we call, again, NumPy, my train, how many unique values we have? 10. 0 up to 9 means we have 10 values. So this one gives us the number of classes. How many classes we have? We have 10 classes. Since the number of classes is over than 2, then it's not binary classification, but multi-classification. Okay? Is it clear? What was the che, chu, ma, right? Correct? Che, chu, ma. Oh, sorry, chi, chu, ma. Okay. Chi, chu, ma. Okay. I should have done this long time. Maybe by the end of this course, I could speak Chinese. Okay? You would, Tima? Oh, no, sorry. You say yo, when. Yo, when? Tima. Okay. Yo, when, Tima? No. Okay. Mayo. Mayo. Do you need me to repeat? Let's see, anyone has a question? No question. Since yesterday, thank you, sir. You're welcome. Okay, so now we know this is multi-classification problem. We understood our data set. And then we come to the first step. After we load our data, we need to create the model. So now in order to create the model, what we need, at least you need always remember we need input layer, then one or more hidden layers, right? And then output layer. So let's start with the input layer. But before that, just we create our model by using the class sequential. Sequential means we are creating type of model where the layers are going to be added in sequential manner. So we prepare our model as sequential, then we start add our layers. So the first one is going to be our input layer. So inside KRAS, you have definition for input layer, and then you need to specify the input shape. So the input shape, again, just you check back the shape for your X train. So X train is 28 by 28. Again, don't be confused. The first one is indicating the number of pictures we have. We have 60K inside the training data, full training data, where the size for each picture is 28 by 28. So we copy this, we put it here as input shape. Okay? Abu, how? Okay, this one I remember very well. Okay, now forget about this for now. I'll come back to this. Then we need to create our hidden layers. So we're gonna create our hidden layers, and notice we are using the definition for dense layer, and then we specify the number of TLUs, the number of units. So here meaning we have 300 units inside the first hidden layer. Okay, so 300 means the number of neurons. Then the activation function is ReLU. Why it's ReLU? Again, you can refer back to the slides. You can refer back to the slides. When you work on hidden activation function, then you need to use ReLU. Okay? At least for now, this is enough for you to understand. Then followed by another second hidden layer where the number of neurons is 100. And the activation function is same ReLU. Finally, by the way, here for those two, it's up to you. You can tweak the values. You can have 300, 400. As I said, you can refer back to the slide. Okay? Now we have the output layer. Then we define, it's another dense layer. And the number of units here is 10. By the way, here you have to be decisive. That means you need to be careful to assign the number of units here. For the hidden layers, it's up to you. You can follow the typical values. But when you come to the output layer, you have to make sure the value you put is correct. So now here, since this is classification problem, correct? If you check back the slides for classification MLPs, then when we look for the number of neurons for output layer, multi-class classification, 1 neuron per class. How many classes we have? 10 classes, correct? T-shirt, ankle boot, and so on and so forth. We have 10 classes. This is why we put 10 here. Again, here you have to be careful. When you assign the number of values, it depends. You can check back the slides in order to determine the right number of neurons. And then the activation function is softmax. Again, check back the slides. If you are looking for the output layer activation function for multi-classification, it is softmax. Why it is softmax? Because softmax will ensure the probabilities coming from all the neurons, the output neurons, the probabilities, if you sum them up, they should be equal 1. This softmax ensure that if you sum up all the probabilities from all the output neurons, they should be equal 1. But logistic, not necessarily. Okay? Now we come to this one. Why we have added flatten? The answer is, firstly, what is flatten is, before I say why. What is flatten? Our data set here, the pictures are in how many dimension we have for the pictures? Are they 1D, 2D, 3D? If they are 3D, then we need to wear the camera. I mean, those glasses, right? Is this 3D? No, right? Is it? It is 2D. How I know? Because again, it's 28 by 28, 2 dimension. They are 2D. So since they are 2D and we are using dense layer cannot work with 2-dimension photos. They only work with 1-dimension photo. That means all the photos has to be presented as vectors. Okay, so what does that exactly mean? If we go to MS Paint, let me explain to you. So assuming this is our picture, for example, this one. And then assuming I got only 6 pixels inside my photo, only 6 pixels. If you have any objection, tell me, huh? I can make it more, but I think 6 pixels is enough. Where's the brush? Here, the brush, and then let's choose different color. So let's say this is the first pixel we have appears on the screen. This is second pixel we have, third pixel, and then fourth pixel, fifth pixel, and the last pixel. So this picture is 2D, 2 dimensions, since it has width and height, correct? Since it has width and height, this is 2 dimension. And all pictures like this, all pictures you watch on your Facebook or even on your computer, all of them are 2D. Unless if they are 3D, then you need to wear spectacles or glasses, special glasses. Now again, dense layer cannot work with 2-dimension photo. This photo has to be presented in 1 dimension. This is why we add flatten. So flatten is going to do the following. Flatten is going to do the following. When we apply flatten, F flatten, then my photo is going to look like this. Now we take the first pixel. So the first pixel is going to be here. Second pixel here. Third pixel, the blue one here. Now we finish the first line. The following line, the second line is going to be placed right after the blue. Then following by this, but just I didn't manage the space enough. And finally, we have the green one. Maybe we can fix it a bit, make it nicer. Okay, so understood what's happened? So we convert our data from the picture from 2D. So this was 2 dimension to 1 dimension. Okay, understood? What does flatten do? Anyone would like to take picture? Selfie also can, if you like to come take selfie. Okay, so again, why we need to do this? Because the following layer is dense layer. Dense layer cannot work with 2D. They have to be in 1D. So this is why we added here flatten. So flatten is just simply is going to take the input layer, the input shape, since it is 2D, and is going to convert it to 1D. Okay? Clear? Yo win, Tima. Then after you create all of this, again, is just by creating our model, nothing else. If you like to inquire about the summary for your architecture for this neural network, you can call summary. Okay, now we come here. How many layers we have in all in this model? We have 4. Input layer, 2 hidden, and 1 output. So same here, you see you have 4 layers. The flatten, and how many inputs we have here for flatten? After flattening 28 by 28 pictures, they become 784. Why? Because if you multiply 28 by 28, you're going to get 784. So the total number of pixels inside each picture is 784 pixels. By the way, 784 pixels, that means later when I need to feed the neural network, the input layer, let's just type in input layer. How many inputs I have? How many inputs I have? $784. That means we start from, let's say this is X1 up to X784. Okay, clear? Sorry, what was clear? J, wait. I have to practice. No, this is wrong. Second one. J Chuma. J Chuma. Is it clear? J Chuma? Okay. Yo. Great. So these we're gonna have 784 input. It's gonna be fed to the following hidden neural network, the hidden layer. And this hidden layer has 300 neurons. And the second hidden layer, we have 100 neurons. And finally, the last output layer, we have 10 neurons. Now, if you check here, we have another column called parameters, param. Now, for the first input layer, we have no parameters. Parameters mean the number of weights and biases, right? Remember, we have bias and weights inside any neural network. If you forgot, we have weights and bias, correct? So actually, these are the parameters that we are trying to tweak to identify their values. So now back here, how many parameters we have for the input layer? 0. Why 0? Because input layer has no preceding layer, correct? So that means it has no weights. If this is the input, so this is one neuron, the weights coming from the preceding layer. Now input layer has no preceding, correct? So there's no weights, no bias. So this is why we got 0 here. Let's go to the next layer. Next layer we have 300 neurons. How did we get the number of parameters? 235500. In other words, 235K. Any idea? That means we have this number of parameters as weights and bias. Anyone can prove how we get this value? Anyone can tell us how to calculate? Anyone? Now, for this one, we have 300 neurons, correct? 300 neurons. But where the inputs will come from for this hidden layer, they're coming from the input layer, right? Hello, guys. So this hidden layer has 300 neuron, and those neurons are getting their inputs from the preceding layer. The preceding layer is the input layer. How many inputs we have? 784. So now if you multiply, since it is fully connected, remember, dense layer fully connected, then 784 multiplied by 300, we get 235K, but only 200. So we are missing another 300 value. Any idea where we can get the 300 values from? Parameters? From? You remember we had bias. I didn't calculate bias. What is bias? Again, refer back to your slide. Bias is extra input, correct? Like this case, we got extra input. So now checking back here, the inputs for this hidden layer is 784. Add 1 for the bias because we have bias. So again, let's calculate 784 plus 1 becomes 785. Multiply by 300, then we get 2,335,500. Because we have extra input from the bias. That means each neuron is getting 784 pixels plus 1 pixel or 1 value from the bias. So actually each neuron from the first hidden layer receiving 785 inputs. 784 from the image itself and 1 input extra for the bias. Okay? Clear? You would team you win team up? No. Let's go to the next one. Let's see if you now can calculate this one. How many parameters here we have? Let's calculate. Now here we have 100 neurons. So we have 100 neuron multiplied by how many inputs coming from the preceding layer? Come on, guys, you are almost dead. Yesterday, I enjoyed my time more than today. They were talking a bit. What's happened to you? Say something. What to say? Say anything. Doesn't matter. Sorry? Okay, 300. Yeah, so 301, because 300 coming from the output of the preceding layer, the hidden layer, plus 1 for the bias. So multiply by 301, then we get 30,100. Okay, let's try the last one. The last one is easy. So we have here in the output layer 10 neurons multiplied by how many inputs? 101, right? So 100 from preceding plus 1 for the bias. So 101, they become 1010. If you sum up all these values, you have 266,610 parameters. Is this big number? Is this big number? Actually, it is. By the way, if we take an example just to show you how big this is, assuming we are using linear regression, which is wrong, but just for the sake of argument. For the sake of argument. Or let's take simple example. If you go back to your assignment, how many input features you have? I think you had 6, right? Let's say 6. I cannot recall exactly. Let's say you have 6 inputs, and you are interested to apply linear regression. So linear regression, what is the equation for regression? You remember the line equation? Y equal to I stuck. I need some push. Equal to nobody. Equal to last time, last call before departure. The general line equation is y equal ax plus b, right? So now for a case where you have 6 inputs, what the equation is going to look like? Y equal, let's say a1 multiplied by x1 plus a2 multiplied by x2 plus a3 multiplied by x3 plus a4 multiplied by x4 plus a5 multiplied by x5 plus a6 multiplied by x6. Finally, do we have any final for the bias? Plus x0. Or we call it here a0, because we're looking for the bias value. Okay, multiply by x0, no worries. Then x0 equals 1. So in total, how many parameters do we have here in this case? How many parameters? By the way, x1 here is like the longitude. x2 is the latitude. x3, let's say occupancy. x4, blah, 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 and so on and so forth. So how many parameters we are looking for? Linear regression is going to find the values for these a1, a2, a3, a4, a5, a6, and a0. The total number of parameters, only 7. If you are using linear regression in your assignment, linear regression is only trying to find the values for 7 parameters. That's all. Okay? While here, for neural network, you see the value? How many parameters? It's about like quarter millions parameters. So this is why neural network requires a lot of computation power. It's not like running normal algorithm. This is why, again, neural network exists long time ago, but it wasn't feasible to apply the concept because they didn't have strong machine. And also, of course, not much data to train neural network. Okay, now we're done with this part. Now, if you like to recall about the layers, to get the objects, you can call layers. If you like to get reference for, let's say, the first hidden layer, then you provide the index number for the hidden layer is 1. Then you can call the weights. So here you can get all the weights initialized and the bias as well. So the bias at first, they are just 0. And here some random values for the weights. Now, all of this is just about creating our model. Now we need to come to the next step, which is to compile our model. In order to compile our model, we call the function compile, and then you need to provide 3 values. The first one is the loss function, optimizer, and metrics. So since we are working on classification problem, then we need to use cross entropy. Since it's multi-class, then it is sparse categorical cross entropy. You can also check your slides. It gives you some hint, but it may not be enough. But anyway, this is cross entropy. So you need to use for loss function when you use classification. The optimizer is stochastic gradient descent. So just we type SGD. And then the metric, since it's classification, then we can use accuracy. If it's regression, then you can use mean square error. By the way, if you are using regression, then the loss function, you cannot use cross entropy. What you can use? You can use mean square error. Okay? You can use for regression, the loss function, here you should change to mean square error. Again, why we need to provide loss and optimizer? Because optimizer is helpful for what? To tweak those values. Is going to adjust the weights and bias. This is the duty for stochastic gradient descent, the optimizer. The optimizer is going to change the values for these parameters. But in order for optimizer to decide how to change, whether, for example, let's say the current weight for one of the neuron is 0.5. Shall it become 0.55 or maybe 0.45, decrease or increase? Then we need loss function. Loss function is going to provide us some value. This value, stochastic gradient descent, is going to depend on in order to decide how to tweak the weights and biases. Clear? During the back propagation, remember this backward pass. So during forward pass, these two are not useful. During forward pass, because if you remember back propagation, we have 5 steps. Forward pass, correct? So during forward pass, loss functions, stochastic gradient descent are not needed. Only when we come to the second step, then we need to calculate the loss function value. And this loss function value is useful when we start the back propagation during backward pass. So it's going to read the loss function value in order to update the weights. Is it clear how it works? And you see this function or back propagation is there since 1986, before even you were born, right? So again, neural network is not something new. It exists long time ago. Any question? Yo, Wen, Tima? Again, if you like, please don't be shy. Just go and write. Okay, here we got a question. Finally. Sir, the output layer, we put the class size, which is 10. Yes, correct. So if you are working on classification, again, you can check here. If you work on classification, then in order to determine the number of output neurons, you need first to identify your problem, whether it's binary or multi-label or multi-class. This is multi-class, then we check. How many neurons we need? It's 1 neuron per class. How many classes we have in this problem? We have 10 classes. Again, if you don't remember, you can check the definition, the description for the data set. This data set has 10 classes. You see, the classes are 0, 1, 2, 3, up to 10. We have single label. Single label with 10 classes. Since we have 10 classes, then the number of output in neuron must be 10. If we have here only 5, for example, assume that we don't have sandal and shirt and etc., only 5, then you need to put 5. If you have 3, then 3. If you have million, then you need to put million. Well, million is too much. I think your data set must be in terabytes. I don't know how much is the size in order to train for that much size of classes. Okay. If you still have doubts, please have a follow-up question. You can keep writing. No worries. Then we come, what activation function ReLU mean? Okay, activation function ReLU, I'm not going to explain. If you like, you can look, but this is the common function to use for hidden layers. So ReLU is one of the common function for hidden layers you can apply in neural network. Okay, if you like to understand what is the difference between ReLU, softmax, how they look like, logistic, we have Hover as well. Then you can, Hover, yes, you can use Hover as activation function. Then you can look on the internet what is the difference between them. Okay? For now, it's enough. I'm not going to ask you what is ReLU or etc. But just you know that when you need to apply, let's say for hidden layers, then you need to use ReLU. This is the common one. If you like to read, by the way, you can refer back also to your textbook, and chapter 11 talk about another also hidden activation function. But for now, no need to dive there. Just let's stop here. Okay. Again, if you still have a question, please, you can still type your follow-up question. Even for those who I have already answered your question, if you still have doubts, write your question again. Okay, where were we? Okay, so now this is to compile. Again, this is, we done nothing now, by the way. This is just creating our model, and then we compile our model. That's all. The training time comes when you call the function fit. So now in order to fit, we call the function fit, then we provide our training data, and then we provide the epoch. What is epoch? Do you remember from the lecture what epoch is? What epoch is? What epoch is? Epoch. You can ask ChatGPT. See what it says. We put 30. 30 means the neural network is going to study or train on the training data. Which training data? This one. X train, Y train. Fully 30 times. That means each picture from this training data set, how many times the neural network is going to study? 30 times. Each picture is going to go through, neural network is going to go through it 30 times. Okay? Is it clear? So again, epoch is the number of times the neural network is going through the entire training data. The entire training data. Then we come, this is why we provided earlier, we splitted our data into validation set. So here you can pass the validation data as well. So that the neural network can do validation after training for each epoch. For each epoch, it's going to calculate the validation score. Now, if we call training, see how it works. So again, epoch 30, and then start epoch 1, the first training. Now going this one complete cycle for the entire data. Okay. Seems like there's something wrong. Must not be NaN. Maybe I missed some lines I didn't run, so that's why it's good sometimes to run all. Again, by the way, it's good to use GPU. So if you look here, I'm using GPU. If you have gaming laptop at home, like NVIDIA with NVIDIA graphic card, then should be fine. If you have AMD, I think won't work, but you can check Google or just use Colab. Okay, now sounds good. Okay, notice now in each epoch how the algorithm is working, the training algorithm is working. So it is calculating the loss value function and the accuracy, and also the validation loss. Since we provided the validation data, so also it's going to calculate the validation loss, the cross entropy for validation data set, and the accuracy as well. Okay? So this one is based on training data. The loss and accuracy here calculated for the training data, these for the validation set. What you can notice here, we started with loss value 0.7. As the epoch, as the algorithm or the neural network is being trained, the value will drop down. So 0.7, 0.4, 0.3, and so on. So the loss function should drop down. So stochastic gradient descent will check the loss value, and the objective for stochastic gradient descent is to lower down, to reduce the value for the loss function. Okay? Accuracy, of course, you're going to see that it's getting increased. So we started by 76%. Now we are 89% accuracy. And here it gives you the estimation. You see how long time it takes you. So here it takes for one step 5 milliseconds. For the complete cycle, 9 seconds. So scanning the entire data set for training, it took 9 seconds. The following one, 7, 6. Anyway, we don't care, but just to understand what's going on. You see, loss function keeps dropping down. Accuracy keeps increasing. Okay. Yo when, Tima? Okay. We're almost done. So after training, when you come to the final evaluation, remember like in CRISP-DM, same way, when we approach the final evaluation. When you come to the evaluation phase, then you can call the evaluate function, providing the test data set. And finally, we can do prediction. For this one, let's take a look after the training, the model has been trained. Let's print out the picture, what we have inside the test set. So what do we have here? If we don't know, again, we can check Y test label, and then classes, class names. So this one is ankle boot. Okay, so I'm going to pass this picture to the neural network and see whether it's able to recognize or not. So I'm going to put here just X test for 0. Okay, now what we notice here, how many values did we get for single photo? How many? Just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why 10? Why did we get 10 values? Because it's like this, right? Because we have 10 neurons for output layer, correct? You remember here, we had 10 neurons. Each neuron represents one class. So in other words, the first neuron is going to be representing what? The first neuron representing t-shirt. The second neuron for trouser. The third neuron for pullover. The fourth neuron dress, and so on and so forth. Is it clear? So we have total 10. Now, when you request from neural network to predict for classification in this case, it's going to give you what is the probability that this photo is t-shirt. So here it tells you the probability, the first neuron tells you the probability is 0%. The second neuron for, what was it? I forgot. The second neuron for trouser. So again, what is the probability that this photo, which is ankle shoes, resemble trouser? Also 0%. The third neuron for pullover says also 0, and so on and so forth. The last neuron is for ankle shoes or ankle boots. It tells us it is 95%. So after all, how to determine what is the final output? You look for the highest probability. The highest probability comes from the last neuron, correct? The last output neuron, which has the number index 10, for 9. 9 means, as we said here, if we check 9, it is for ankle boot. Okay? One more thing, since we use softmax, I told you the sum up for the probabilities must be equal 1. So you can try. Put dot sum, and the value is going to be 1. This is because of softmax. If you are using logistic, not necessarily. Okay? Is it clear? Why we need softmax for multi-class? Nobody asks. If you like, then you can ask or raise the question. Otherwise, I feel almost dead. But you still can ask. That doesn't mean you cannot ask. Okay? So I hope you got at least some introduction idea about neural network. Of course, things are more complicated than this, because how to train your algorithm can be more complicated than just like following this example. But this is good starter example to understand neural network. Any question? Any question, guys? No question? Are you sure? Okay, then, since no question, that's all for today. Let's see before you dismiss. No question. Okay.